Scientists postulated a novel Earth's deep interior theory in the 1970s. They suggested it is gently churning like a lava lamp, with buoyant blobs rising as plumes of hot mantle rock from Earth's core, where materials move like fluids. The hypothesis states that these plumes melt as they approach the surface, causing huge volcanic explosions. Geologists had almost abandoned the hypothesis of plumes due to a lack of data. We now have this evidence in a paper published today. New Zealand is on top of an ancient, enormous volcanic plume, according to our findings. This process creates volcanic activity and is crucial to the planet's survival. Large underwater volcanic eruptions about 120 million years ago, during the Cretaceous period and the age of dinosaurs, produced an underwater plateau roughly the size of India. The shifting of the tectonic plates over time caused it to fragment. The Hikurangi Plateau is one portion that is currently buried beneath New Zealand. Experts studied how quickly seismic pressure waves, which are essentially sound waves, move through the mantle rocks beneath the Hikurangi Plateau. These vibrations, which could have been caused by explosions or earthquakes, accelerated to 9 kilometers per second. It is well known that these waves, known as P waves, move through the uppermost mantle of the Earth at a pace that is astonishingly constant. About 8.1 kilometers per second, about 30,000 kilometers per hour, the status of the mantle rocks can be inferred from even slight variations from this constant speed. Fast P-wave speeds, 8.7 to 9.0 kilometers per second, have been seen from a depth of 30 kilometers beneath New Zealand's eastern North Island since the late 1970s. The significance of the high speed was not evident because the seismic vibrations detected in these early data were only moving across a tiny portion of the mantle in one direction. The new data, which came from a significant seismic experiment in 2012 that covered the southern North Island and offshore locations, including the Hikurangi Plateau, is far more comprehensive. It demonstrates that, independent of the horizontal direction in which they moved, P waves reached a speed of 9 kilometers per second. However, a thorough examination of the vibrations produced by profound earthquakes revealed very slow vertical vibrational motion. This proves the existence of the elusive plumes by providing important details about how the mantle rocks have been compressed or stretched by the powerful pressures inside the Earth. Scientists have determined that the Hikurangi Plateau's mantle rocks have to be stretched and compressed in a manner similar to how flattening a rubber ball might form a pancake shape in order to produce the seismic speed pattern they saw. When scientists used computers to simulate rising plumes in the mantle, they discovered that the pattern of pancake flattening as the mushroom-shaped plume head extends horizontally and collapses close to the surface was precisely replicated. Likewise, they examined the seismic data from additional marine plateau in the Southwest Pacific region that had undergone seismic research by international teams. Surprisingly, the Hikurangi Plateau's subsurface revealed the identical pattern in both the Manihiki and Ontong Java Plateau. No matter which way they were moving, P waves were moving at the same high rates, but in the vertical direction, they were moving far more slowly. The Great Oceanic Plateau of the Southwest Pacific are scattered today. However, we are aware of their former arrangement, which dates back around 120 million years. They created an area that spans thousands of kilometers and is covered in a thick layer of volcanic rock. According to our findings, the entire area was located above the single head of a superplume, a huge plume that melted over the course of a geologically brief time of a few million years to produce enormous lava eruptions. Only one other location on Earth, Siberia, has seen this pattern of P-wave velocity in the upper mantle. And it turns out that some 250 million years ago, this was the site of extensive volcanic eruptions that were considered to have been brought on by the emergence of a superplume. This volcanic activity may have caused a mass extinction that impacted the evolution of life and altered the temperature of the planet. The remnants of what was once an incredibly powerful geological force are where New Zealand and a few other dispersed islands in the Southwest Pacific are located. Our novel seismic method for locating these superplume remnants may help us learn more about this process, albeit we are unsure if it is still in progress. This would give us more understanding of the numerous linkages between our planet's deep interior and what occurs on the surface. Likewise, scientists from New Zealand have discovered a vast area of volcanic lava that is about the size of New Zealand and was created by a subterranean continent that stretched out like pizza dough over a period of 40 million years. The discovery is one of several remarkable discoveries presented in a new study that defines Triuamui or Zeelandia, the planet's recently recognized eighth continent, while also providing additional proof of the colossal breakup of the supercontinent Gondwana. The study, which was published in the academic journal Tectonics, also represents the first complete mapping of a continent's subaerial boundaries, whether it is Zeelandia or another. The world's youngest, tiniest, and thinnest continent is essentially invisible to us because it is almost entirely submerged. The largest section of it above sea level is New Zealand. However, if the oceans were to be drained, we might observe it spreading across the South Pacific in a 5 million square kilometer area. The Earth's spreading mass once rose above the oceans for a very brief period of time in its history, sending plants and animals from here to New Caledonia and the east of Australia. Its gently rolling, devoid of mountains, low-lying landscape was home to dinosaurs, notably the enormous titanosaurs. While there have been scientific studies and reports about Zeelandia for more than a century, it wasn't until a groundbreaking GNS-led study in 2017 that somehow made Zeelandia a genuine place and instantly caught the attention of the globe. An international team sailed on an excursion to New Caledonia to collect sea bedrock samples, which was funded by the Australian government and co-led by the University of Sydney, just before that report was published. 6 years later, GNS science geologist Dr. Nick Mortimer and other researchers discussed what they had discovered about them and the broader tectonic history of our globe. Scientists turned to the north, namely the undersea region between New Zealand, New Caledonia, and Australia, after mapping the geology of Zeelandia's 1.5 million square kilometers southern half. Determining the borders of the Earth's continents was difficult because they all have submarine shelves that are mostly submerged. In fact, there are still a lot of unresolved places on geological maps of the planet's surface. Scientists had an even greater hurdle while trying to map the expanse of Zeelandia since its continental shelves were larger and more concealed than most, with only 5% of its mass poking above water. A large volcanic zone that is considered to have erupted along the edge of the Gondwana supercontinent between 160 million years ago was discovered by scientists as a result of their investigation. Magma had previously been underappreciated as a factor in the separation of Gondwana, according to study co-author and GNS scientist Dr. Wanda Stratford. We can see that these lavas now cover an area of the continent that is about the size of New Zealand itself, at 250,000 square kilometer, the scientist said. For the first time, Mortimer continued, we realized the extent of the magma eruptions of different ages imprinted across different parts of Zeelandia. Strong magnetic traces detected during bottom surveys allowed for the discovery of the newly characterized volcanic regions, which were mostly submerged. It's interesting to note that the same magnetic lava rocks discovered here may also be found on New Zealand's mainland, close to Cape Reinga, Blenheim, Hokitika, and Ashburton, as well as in New Caledonia, the Chatham Islands, and Auckland Islands. As Zeelandia tore away from Gondwana tens of millions of years ago, molten magma poured out of fissures and cracks as the continent stretched and thinned like pizza dough, according to Mortimer. This process left behind these rocks. The latest research also emphasized Zeelandia's sloping, 250 million years old backbone, which is made of ancient granite and stretches 4,000 kilometers to New Caledonia. A crucial component of Zeelandia's puzzle, the backbone known as the median batholith, was eventually delineated using materials taken from Fairway Ridge close to New Caledonia. Mortimer, who has been writing about Zeelandia's physical characteristics and makeup for 2 decades, claimed that the issue was far from being solved. Even though the continent is the first to have been fully traced out to its undersea boundaries, there is still plenty to explore and learn, including when, how, and why the great geological events that have shaped our continent occurred. After recently reconstructing Zeelandia's 100 million year development in a series of new maps, GNS scientists have now published a new study that is funded by a government grant and a James Cook Fellowship. As John Rees says, one volcano puts out more toxic gases one volcano than man makes in a whole year. And when you look at this climate change, and when you look at the regular climate change that we all have in the world, we have warm and we have cooling spells. You can suggest topics you want to see next in the comment section below. Please subscribe to Weather Collapse if you want to know more and be updated on the latest news about natural calamities or disasters happening all over the world, and don't forget to like today's video. We'll see you in the next video. Thanks for watching.